When we speak about IPR, CPR, and PR, we are speaking about the combination of two charts, or it refers to
It's just one curve. Yeah, just one curve. So we really have managed to cover quite a lot, now in 2 days. This is the third. And I thought, we really equilibrium is the most, one of the most fundamental concepts in production. Okay, so I wanted to push it very quickly in front of you. And gas, to be honest, is also a bit complex because the properties change. Okay, if we do it with liquid, we can assume that the properties are constant with pressure, and we don't have that complexity. So, but I hope you are kind of understanding. That's why we have the exercise, okay? Because you have to, the information I give you here, then you have to practice. We do it partly here, but then you have to go by yourself and you have to try to, that's where you get, that's where you fix the knowledge in your brain, okay? When you do and you try to practice and reproduce what we have done in class, okay? So we are still going to come up, it's not that we are done, okay? We are going to go back to different types of equilibrium, other curves, but so don't be worried if you still, there are some things that are not completely 100% clear. So we are going to go back to it, okay? Just let's do a small comment on the exercise. Okay, so far we have 3 exercises. I will show briefly here. Okay, so we have exercise 1 is based on the exercise that many of you didn't do right in class, but it's on the production manifold. But this is for a subsea system. Okay, so we have that field. You have the features. That's a field in the Norwegian continental shelf in Norway, offshore. But you might have a similar layout if you are going to start developing fields like Coral here in Mozambique. You will have a similar arrangement. Okay, and we are going to focus mainly on this guy here called volume. Okay, you're going to neglect all the rest. We are going just to see what happens with volume. And volume, the way it is made is that you have a center called a manifold, right? This guy here, that's the manifold. And then from the manifold, you have a line. You have here 2 lines. I will explain later why. But you have one line that goes all the way to the FPSO. Okay, one pipeline. And in our case, will be like you have a separator here. Okay. Now to this manifold, you have 3 wells. Okay, this well, this, and that. That's just a water injector. This guy here. Okay. Actually, the yellow line is the gas injection line. So that's to give gas lift. These wells, they have gas lift. We will see later what that is, but just that you inject gas into the well to be able to lift it to produce more. Again, the blue line is a water line where you send water to be injected on that well. Okay, and you have around that, so you have all wells, these 3 wells from volume, these producers, they are connected with a line to this manifold. Okay, and I'm going to show you that's one way where that's one subsea architecture. There is another one where the wells are inside this we call, well actually it's not called manifold, but it's called, so it's called manifold, but it's called manifold template. Okay, it's a subsea template. Okay? Which is just a metal structure where I have different things inside. I can have a pump, I can have a meter, I can have just a header. Okay, so if you want to send all of them through one pipe, okay, there is only one pipe. What do you need to have inside this box? I wake you up in the middle of the night and you have to tell me, how do I commingle production from many wells? I use a header, right? The header, cabezal. Okay, so I have a header, and the header is connected to that pipeline, and I have all these wells coming to that header. Okay, the way that it looks like, so usually this well is by itself, is like, when you see it from the side, it looks something like that. Okay, you have the seabed, and then you have the well, and then you have a big box, okay, which is the Christmas tree. It's bulky, okay? It's not anymore just the valves. If you're onshore, you see all the valves very clearly. Now it has to have a protective structure, it has to have something where I can operate using a ROV, okay? Sometimes they send a robot, which is like a box to do things. It has some arms to do things on the structure. So it has a panel so that this robot can use to open and close valves. So it's a very complex structure, okay? And I think I have a figure. Let's see here. Okay, it looks something like that. So it's not anymore just a simple collection of valves, even though they are behind. Okay, behind all of that, they are there. Okay, so there you see, you have the conductor, okay, coming up from the ground. The conductor is holding this Christmas tree. Okay, and then you have the whole Christmas tree, where you have this panel that I told you, the ROV can come and close. I want to close the choke, I want to close the wing valve, I want to close the master valve. The ROV can operate basically everything from here. And you will see Subsea, there are a few more things we need to have there. Okay, if we have gas injection in the well, if we have water injection, so we can have a bunch of additional valves there. Okay, but you see here, what I have here to the left is a template. Okay, which is that, let's say it's a manifold, okay, where I have my header that is just collecting the production from different wells. So the connector, some cases, if they are very close, I don't use a pipeline, okay, because for the pipeline I have to lay it on the ground, then I have to support it, I have to maybe dig a trench, okay, I have to do many other things. So I use this device that is called a jumper. Okay, so this device here is called a jumper. Okay. And basically I hold it with some cables, I lower it down, and I make the connection on the wall side. It has a vertical connection, which is very easy to make. You have no friction, right? So it goes down, and then just with the weight, it latches on that connector, and also on the manifold side. Okay, so in that case, the manifold or this template will have, three of these, okay, three latching places. And these jumpers, they can also be horizontal. Okay, you can also make the connection horizontal. But vertical is usually preferred when you have deep water. Okay, when you have deep water, then it becomes very difficult to handle, and you want to have gravity on your side. Okay, not working against you on a horizontal connector. Okay, so what I'm asking in that exercise, I'm saying, well, this pipeline is, I think in that case, is like 15 kilometers, okay, long. So it's long, and it's subsea. The water depth is, I think I give it on the exercise, is not very deep, 130, but it costs, okay? So if you want to put another pipe, okay, because you can do it. In some cases, for example, in Brazil, is required by law, okay? You have to test using a test separator. So this is on top of the ship, right? This separator is on top of this ship here, Alpine. And then I have to put another separator, right? And then I have to put another line from this template, 2 lines. One will be the test line to take it to the test separator, and one will be the production line. Yes? And then I have to put inside, I have to put another header, which will be the test header. Yes? Can you speak a bit higher? Because I cannot hear you very well. Yeah, the fluid is being produced from these wells, okay? This is where you have the hole in the ground. Then you have your well, and then you have in your boat, you have your separator, all of your processing facilities, separator, pump, etc. Okay, so you have to take it from the well, which is subsea. Okay, you have to take it to this FPSO. So you put a line from there all the way to the FPSO. Okay, now you don't have subsea separator to test. This is subsea. So any separator you want to put to test, you have to put it on top of the same boat. Okay? And then you see, well, to reach that separator, I don't want to interrupt the production from all the other wells. Okay? If I want to test this well, for example, if I want just to test the production from that well, if I have just one line, I will have to stop the production from the other two to measure. And that costs money. Okay? If this one is producing, each one is producing 10,000 barrels a day, and I tell my boss, oh, I want to test. Okay, let's go one day, let's just shut these two down. Okay? I'm going to get fired for sure. Okay? They're going to calculate my salary, then say 10,000, 20,000 times $80 times 24 hours, you're fired. Bring me another guy that knows how to test. Okay? So in that case, it's much cheaper just to put another line, okay? And then here you have to put the same thing we have done in class, okay? You have to put 2 headers, okay? One test and one production. Yes?
You mentioned that in Brazil, is the demand from Brazil, it's above from Brazil, or is the condition that?
Yeah, that give me just a sec to explain that, okay? So until very recently, the only test method approved by the government, by partners, by everyone, is using test separator. Okay, it's the only method allowed. If I want to split the cake, get to find this magical factor between them, I can use only a separator, a test separator. Okay, only recently, like in Norway, they say, well, now if you measure with a multi-phase meter, it's a meter where you can send all 3 phases. Okay, you don't have to separate, because what they do in the separator, they measure gas and oil separately. Okay, when you put it on a multi-phase meter, you have all the 3 together: Q oil, Q gas, and Q water, and then you can measure that. Meter can somehow measure how much you have. Okay, but that technology, we are not going to talk too much in this course, but it's still, people don't trust very much on that technology because it's very new. They say sometimes they say it's immature. Okay, it doesn't give you good results. So in Brazil, if you're going to develop this field, they test by law that you have to do it using a separator. And if that's the case, you have to put 2 lines. Even though the distance is 50, 100 kilometers, you have to use a separator. And it's by law. You cannot just put the 3 of them together and mix it in a long flow line. You have to know how much each well is producing by law. In Norway, and this field is in Norway, okay, they say, well, we trust this multi-phase meter. We want you, the people developing the field, I think my keyboard there is not working. Oh, yeah, I think. Um, okay, in Norway, they have had a lot of experience with these meters, and they say, well, you don't have to put the extra line. Okay, we trust your multi-phase meter that you're going to use. Now, they say, for this example, we want to place a multi-phase meter inside, let me just, okay, I want to put a multi-phase meter inside that manifold, somehow. Okay, so the manifold, if or this template, if we look like in detail, we have three wells, right, coming in. We can say these are three wells coming in. Okay, well one, well two, well three, and we have one line coming out, which is the to the FPSO. FPSO stands for, any of you knows? And offloading, yes. Okay, floating, production, storage, and offloading. It has like all the functions: floating, is not platform, floating, production, storage, and offloading. Okay, but there inside you have a flow meter. Okay, you have one component, Norwegians trust it, and they say you are allowed but you have to test each well, but you're allowed to do it with a multi-phase meter. Okay, so you have to find a way to send the production from well 3 at will, okay, to send it through the meter and through that line, or well 2 through that meter, through that line, and well 1 through that meter and through that line. You have to find a way. And I'm not going to spoil all the fun for you, okay, but I'm just going to say you need to have a header. Okay, you have, this is the production header, okay, and that's connected to this line. Okay, so if you want to connect to that meter, you need to have, yes, you need to have one line which is maybe like that. Okay, and here, what do we have to place in between the meter and this header? This check valve, right? We don't want to have backflow. But then we need to find a way to send the production from this well, for example, to that side. Okay? Okay, so let's do a bit more. So first we need, remember what we had for the case of the onshore manifold. Okay? We had, what did we place there? Two valves, right? If you remember. It was a long time ago, so I myself don't remember very well. Okay, so you had one valve here, right? And then you had one valve there. Okay, and depending if that's closed, then the flow will go through there, or if that's open, that one is closed. Okay, then it will go to production and it will go to the rest of the FPSO. Okay, now I can just send directly here to the meter, and I can decide to test. Okay, I can decide. Okay, if I just don't want to test the well, just want to produce it, I send it through the main production line. That's it. Or if I want to test it, I close this valve and I open this one and I pass it through the meter back to the header and then go back. Okay? So I have almost solved the exercise for you. Okay? But you have to do it also for the other wells. So you don't need to have just a line, but you need to have another header. That will be the test header. Okay, so just keep in mind this small clarification that you not only need header if you have two lines and two separators. You can also have two headers for all kind of reasons. Okay, for routing, for metering, for all kind of things. Okay, and placing, especially in that case, placing another line subsea is very expensive. Even though it's 130, is very expensive. 1 kilometer of pipeline, I think it's in the range of $1 million. Okay, to lay a 1 kilometer of pipeline. So it's a very expensive operation. Okay, so you have to, that's for exercise 1. Okay, you have to make that, and I just wanted to clarify, that sometimes jumpers are used like here. Okay, that will be a jumper to connect. There is another type of architecture, pretty much, so this is pretty much used everywhere else in the world. Okay, in the Gulf of Mexico, it's used in Africa, it's used in Indonesia, but in the North Sea and in Norway, they're a bit special. So they use something different. And they use it also a bit in Brazil. Okay? They use, so that's this configuration is what is called satellite wells. Okay? Wells are satellite from the manifold. Okay? From the template, satellite well. But in Norway and in the UK and in Brazil, for example, and some other places, they use cluster wells, okay, or template wells. And in that case, is that in the same structure, they place the wells in the same subsea template. They place the wells and the manifold, both in the same subsea structure. That's just to try to save money. Okay, they don't want to have here. You need a lot of structures. You need 1, 2, 3, and then you need the structure of the manifold. In this case, they try to put everything under one. Okay, and the way it is done, they place wells in a different compartment. Okay, they have their own compartment, and usually it's a template of 4, but they have templates of 6, 12, 8, whatever. Okay, and here in the center, they put the manifold. Okay, so I'm going to show you very soon a picture. And here is where you connect the flow line that goes to the FPSO or to the separator. Okay, and that will be well 1, well 2, well 3, well 4. And all of them are connected to this manifold. And what do you have in this manifold? The header. Okay, now you're getting either brainwashed or you are understanding the idea. You're going to finish this course, you're going to be having nightmares on flow equilibrium, header. Okay, and I think that's partly the intention. Okay, so you have to have one header, right, where you commingle all of that, and finally you have the connection to the flow line. And in that case, it's just a piece of pipe. Okay, so I'm going to show you a figure, and we are going to try, or I'm going to ask you if you understand what are we looking at. So that's the template. Let me make it a bit bigger just to show. Okay, so where are the wells drilled? Where do you think in this structure? Okay, you see here you have some holes. This is just to support the structure. Okay, this doesn't take any weight. All the weight from the wells is supported in the conductor, like they should have told you in your drilling classes. Okay, so you have here the holes where you open this lid from the top, and from there you start drilling, put your BOP, run casing, whatever drillers do. Okay, then they close this lid, open the lid on the side, and drill this one, and they. So, what is the main, when we talk about drilling, right? What is the main difference between this type of well and a satellite well, for example? Well, these ones, they are going from the same point in the surface, right? And they are going to reach different targets in the reservoir. So they have to be very much deviated to reach the target they want to get, because they are starting from the same point. Okay, so in this case, these template wells, okay, they start from the same point. Again, then they deviate depending on where your target is. Okay, in the case of satellite, they can be drilled exactly on top of where they have to be. Okay, if there is horizontal or vertical, almost no deviation, and then they connect to this manifold in the seabed. Okay, and there is the equilibrium is someplace in between. Okay, if your reservoir it's just very localized. Okay, it's very compact. Sometimes it's cheaper to drill in one position. Okay, because in each one of them, if your reservoir is very separated, is very spread. Okay, you have to move the rig. Okay, the rig has to drill first here, and then it has to move to the other location, and that movement, it costs money because you still have to pay for the rig, right? It's like staying in a hotel room. Even if you're sleeping there or not, you still have to pay. Okay, if you have your suitcase inside, you have to pay.
What's the advantage of the first one in terms of production?
It's not really. It's much better if you make the well as less complicated as possible. Okay, so is this one in terms of production really? This will be longer, a bit longer, and it will be more deviated. So you have a bit more issues with the pressure drop. Okay, but really sometimes there is not much difference between them. Okay, but this will be longer, so the TPR will be slightly more abrupt.
But in terms of, for instance, do you work with the four wells at the same time? Or one?
No, you do when drilling. You drill one sequentially, one after the other. Okay, and you're not allowed to produce one well while you're drilling another in the same template. Okay, because what happens? The BOP is a very heavy equipment. If you go down and then you knock the structure, you knock another well, then it's a disaster. So every time you're drilling, you're not allowed to produce from any well. Okay, until all the template is ready. So you see here you have the 4 wells, okay, or 4 slots, and then you have one in the center which is called the manifold. And it's a module. I make it such that if there is a problem, I can just replace it and put something else. Let's say that the meter got damaged. Okay, so you can just take out the manifold and then put another back in. So let's see how it looks like. So let's see if we recognize some of the things that we were discussing in class. So I took out the cover of the manifold. Okay. So first, where do you have the connection to the main pipeline that will take it to the FPSO?
Just a quick one. The manifold is the head. The same.
The manifold is the structure that contains the header.
Oh.
Okay? So, yeah, here you have some help. Okay, so where do we have the connection to the main line, to the main pipeline that will go to the FPSO? Do you see it or not? It's here, okay? It's this pipe here. So if you continue upstream, that's where you should have the header, right? Because in all of our drawings, we are making that the header is just upstream the flow line. Okay, so that's what you have here in your drawing. You have this is the main header. Okay, so where are the wells coming into that header? You see, maybe it's not so clear, but you see here you have a connection, here you have a connection from each well, and here. Yeah, you should have 4 connections, right? So here is 1, 2, and you have 2 on the other side. Okay, because the header in this case is like let's try to make a sketch to see if it comes okay. Okay, we have our manifold. Okay, and here we have something like that. Okay, and here we have the connection and the connection to that manifold. Okay? Now, so see, just look at that the pipe is not exactly straight. Okay, if you look at the pipe, how it looks like, this is the pipe that comes from the well. And you see it's not just a straight line, to the manifold. It just has this shape. So why do you think it has this shape? Those of you working with pipeline. Is any of you working with pipeline here? No? So why do I have this strange shape? That creates flexibility, right? Okay, that is because during operations, okay, during the operation of the well, producing or not producing, the well is going to expand. Okay, the conductor, casing, tubing, everything is going to expand due to temperature. If I stop producing, everything is going to get very cold and it's going to shrink. Okay, when I start producing, everything is going to warm up and it's going to expand. And sometimes this change can be in the range even up to 1 meter. Okay, this oscillation up and no, the last, well, I'm 1 meter. I think. Yeah, maybe 1 meter is too much, but I'm sure it's around at least 30 centimeters. Okay. Okay, for some cases that we were working on that 0.3 meters. Okay, so you have a huge expansion and contraction. Okay, and that if you have just a straight line, just a straight pipe, what could it happen? If you have just a pipe that is connected to another pipe here, when this goes up, it's going to break it. Okay, it goes down, or you have fatigue, up and down, and it's going to break it eventually. So that's why we have this strange shape, okay, to give flexibility to the system. When it goes up, it's like a spring, okay, like a coil. Okay, when it starts to go up, it rotates over its axis. No, it's a pipe. This is a pipe. No, it's solid. It's a piece of solid pipe. It bends. Okay, the well, when it wants to expand, the well needs space. Okay, it's like your wife. My wife needs space. Okay, I'm going to take my space. Yeah, I'm going to take that out of the recording. So, okay. So it takes space, but the thing is that if you have a rigid piece of pipe and then you're going up, it's going to break or it's going to fatigue. If you have a coil like that, then it goes up, it's just going to bend it a little bit. It's more flexible than having just a straight piece of pipe. Okay, and here you have, so what do we have here? And you see that the line comes from the well, and then you have two valves. What are these two valves? These are the routing valves, right? If we look back at our drawing, we see that we need two valves, one here and one here. Okay, so these are exactly those two routing valves to see if I want to produce to this header or to that header. Okay, so in my drawing, you have one valve here, and then you have one valve here, okay, to the other side. Okay, we are not going to dwell too much. This class is not about subsea, but I just want to show you how it looks like. You always have the same function. Okay, if you need to send to two places, you have two lines, for example, you need to have two headers. You need to do tests, you need to do two headers. And if you have two headers, you need to have two valves. Okay, so always think about that, and you can almost understand any configuration is used in any system. Okay. Yes. Okay. More or less clear. Okay. You have a bunch of other things that we. So these are valves which are gate valves. Okay, that we open and close with a hydraulic line. Um, this valve is called a crossover valve. Okay, so here in this case we have in our drawing we have a valve separating these two headers. Okay, so I have in this case I have actually two lines coming out. Okay, because for some reason I decided to test having two lines in this particular example. But sometimes I want to open and communicate the two headers, and we will see maybe if we have time a bit later why do we need to have that in place. Okay, it's due to hydrates, and we are going to discuss a bit about hydrates today, but let's leave it for later. Okay, you have a valve connecting, and here it comes from the well. You have this flexible pipe, and you have two valves, and they connect to these two headers. Okay. So now that's the first exercise. Okay, the second exercise we had exercises. Okay, you have to solve this exercise that we have done here in class, and so you have to deliver the Excel sheet. Please put your name and your name. Maybe let's do something. If you want, you can partner up in teams up to 3 people. Okay, if you want. If you want, you can deliver yourself. But if you want, you can group in a group of 3. Okay, how many are we here? Okay, yeah, so four groups. That's fine. Okay, so here you have to resolve this exercise to calculate the rate, and then you have to plot the rate versus pressure, how it looks like. Okay, so that's exercise 2. And it's okay if you send me just the Excel file. So you have to plot QG, which is local. Remember, it doesn't have the bar on top, so it's local rate, gas rate versus pressure. Okay, and if you remember in class, we said, well, it's going to look something like with pressure, it should do something like that. Okay. The plot, please make it nice. Okay, make it. So in the plot, I want to have outer tick marks. Okay, that means these small guys here. Sometimes it's difficult to see if you don't have it. Use a big size font size, okay, something that I can read. So font size usually is something between 14 and 16. Okay. In the name of the axis, put the name of the variable, the symbol of the variable, and put the units of the variable. So if you say pressure, I write pressure, comma, P, comma, bar. And try not to select, so don't use yellow, okay, or any of these colors, like all of these green, which are very light, or pink. Use some colors that are easy to see. Okay, pink, etc. Okay, so that's clear for exercise 2. Now for exercise 3, okay, you have to solve flow equilibrium. That's the one we have done yesterday. Okay, this exercise, okay, and you have to solve by yourself this exercise. So what you have to deliver in that exercise is first, so bottom hole equilibrium, and that means IPR Remember, IPR stands for inflow. Yes. I wake you up in the middle of the night and ask you what is IPR, you have to tell me inflow performance relationship. Or if you don't know the name, you say is the available pressure at the bottom of the well calculated from the reservoir. Okay, I will prefer that answer. So bottom hole equilibrium, IPR versus TPR, and assuming PWH is 40 bar. Okay, and I want the plot. Okay, you have to make the plot. That's the first task. Then the second is wellhead equilibrium. Okay, that's task number 1. Task number 2 is WPR versus P separator. Okay, assuming P separator is equal to 40 bar. And for these two cases, you have to find the equilibrium point. The equilibrium rate and PWF. Okay, the point where the two are equal, and this also you have to find the equilibrium rate, which we know already is going to be the same, right? And then the third task you have is to perform again wellhead equilibrium, but including the flow line, okay? Including the flow line. So that will be the WPR versus the FPR, okay? And find the equilibrium rate and also make the plot, okay? Make the plot here and make the plot here. Okay, that's your mission. If you, well, you have to accept it, right? Yeah, there is this, here you cannot decide, you have to. And we agree that exercises can be delivered in groups of 3, okay? But please try that it's not like one has the brains in the team, does all the work, then another one is just making the cosmetics, okay? Putting the, you have, both have to be the brains, okay? Both of you. So you have to be, if I ask one of your group to tell me how you did the calculation, you have to be able to answer. Yes? Clear so far? We're going to have a few more exercises, okay? I'm going to try to solve most of them or part of them in class, but you have to go home, try to see that you understand exactly what was done in class, do it yourself, and especially making the plots and finding the rate for each one of these cases, it really helps to to fix the knowledge in the brain. We said deadline is going to be 1 week after I leave. So that means on the 10th. So deadline will be for Sunday, the 18th of November. Okay. We will see how you go. If it's too tight, we can maybe extend it a bit. Okay. But tentative deadline is 18th of November. And last year, I think, yeah, you can send it to my email. Okay, send to my email, which is milan.stanko at ntnu. Hmm? Skype? You don't have you don't use email? You,
You have Skype and WhatsApp.
yeah,
WhatsApp.
both. I have both. Yep. My Skype is okay. Stancome. I prefer if you write in WhatsApp in Skype. Okay. I'm still going to get it on the phone, but yeah. Save for another. Okay. Now, um, okay. So we had one more thing pending from last class. Okay. Sorry that I have to, but I think it's important for is in. Okay. We had one more thing, right? That was this subsea safety valve. Okay, so I just wanted to show you this figure. Okay, if you remember, that's a safety valve. Okay, it has nothing to do with control, nothing to do. It's just safety, such that if something happens to the wellhead, I still can close the well. I still have control of the well. Okay, so the name is SSSV. So it's called subsurface safety valve, or is also known as DHV, which stands for is a much easier name, downhole valve. Okay, but sometimes you have valves, you have chokes which are in the bottom of the well. Okay, so sometimes people, to avoid confusion, they say SSV. Okay, and that's what we just another image that to hopefully will be very clear. So you have that line, which has to go through the tubing hanger. Okay, that line, if you remember, the hanger has some holes, so it has to go through it, and then it has to go all along the tubing. If you remember the figure we did last time, you have here the valve. Okay, this SSSV. Okay, so usually about 100 to 200 meters, okay, and then you have this tubing hanger, which is a bit deformed here in this case. Yeah, and you make a hole through this hanger to pass that hydraulic line and send it all very close to the tubing to feed the SSB. It's just a small line, I think it's a quarter of an inch metal that goes sticks to the tubing. It usually has like a strap. Okay, it has a strap here to fix it to the on the outer part to the tubing, and that is what's giving the pressure and is keeping this spring compressed, and by keeping it compressed you're covering that flapper. Actually this one should be all the way to here. Okay, when something happens, here is an emergency, something happens, you lose the hydraulic fluid, then the spring pushes back up, and then that uncovers this flapper, and the flapper closes. Okay, such that if you have fluid coming from the formation, you don't have any more production. And as I mentioned, I think I have here a very, it's not nice, but it's very strong picture why we need to have it in the well. Okay, that's I think taken from Kuwait when was the war in the Gulf. So you see that the wells were burning for a long time. It was just like a mechero, okay? Just like burning without any control. So they had to come and make a sidetrack and kill the well and then control it. A very expensive operation. Okay. Okay, so now finally we can start the topic for today. Okay, and I just want to make a summary of downhole equilibrium. Down. Okay, and in that case we intersect, that's Q of the gas, that's pressure, and then we intersect one curve called IPR and another curve called TPR. And at the bottom hole, if I have nothing in between, I have no pump, no choke, nothing, the two pressures should be the same, and they should give you this is the equilibrium rate, okay, QG star. And why do we use solver? Like I mentioned, we are basically solving these two equations. Okay, and this equation okay, and that equation, those are two equations and two unknowns. So you can solve it analytically even for this case. Okay, you can solve it. You want to know these two guys and you want to know these two guys. So you have two equations and two unknowns. So you can decide, you take one, substitute in the other, you solve it with Newton-Raphson, you take it to MATLAB, whatever you can find many methods. Okay. The truth is, we don't have usually analytical equation. For IPR, yes, but for the rest of the system, not. Okay, we have to do, you don't have just a very nice, beautiful expression like that. Okay, you have to perform like a stepwise calculation. So for those cases, it's better to use the solver. Okay, you create some sort of a solver. You create another function, which is the difference between those two, and then you say that I want to drive to zero, and that will be the solution. Okay, so now what is the effect? Let's say we talked about a few things yesterday. Okay, so let's say first, what is the effect of tubing size, tubing diameter? What will happen? Which curve is it going to affect? TPR, right? So how is it going to affect it? If I make the diameter, let's say, bigger of the tubing, the rate will increase, right? Now I ask you, this point here, is that going to change if I increase the diameter?
Yes.
Yes or not?
Yes.
We have to make a vote, okay?
Yes. For sure.
Okay, let's say I have the tubing, that's my tubing, right? And that's my PWH and PWF. And now I have a big tubing, and this will be PWF and P, well. If I have no flow, okay, the rate is 0. And I have here the same pressure, 40 bar and 40 bar. How should the two pressures be? That's the point we're calculating here, right? We have fixed wellhead pressure, we have no flow, and we want to calculate the static bottom hole pressure. Yes? So are they different or the same? They're the same, right? You have no friction. You can make the conduit 1 kilometer diameter, you can make it 1/4 of an inch. Okay? So that point doesn't change. But we'll start like you say, if you use a bigger diameter, you will get something like that. Okay? So that will be TPR for increasing diameter. And if I reduce, The diameter?
QG.
Okay, we'll go to the left. That's correct. Let me see. If the diameter is reduced. Now, what happens if I change the wellhead pressure? Somehow I go to my separator and I change the controller. I say I don't want anymore to be 40 bar, but it will be 30 bar. Okay, I change this pressure here. What do you think will happen? If I decrease, let's say I go from wellhead pressure, I go from 40, I go to 30. I have a lower pressure, right? If I have a lower pressure, will increase. Remember what drives the Q, okay? The Q is a very complicated function of reservoir pressure and separator pressure. This is the driving force that is driving the flow, right? The difference between reservoir and separator. If I lower this one, the difference will be higher, right? And because the difference is higher, then the rate should be bigger. Okay? That clear? Okay, like let's say here, okay, if I put now 30, what will be the static pressure? Will it be higher than for 40 or lower than for 40? Lower, high, huh? If I have here 30 now, okay, I have no flow. The pressure here is going to be higher or lower than when this pressure was 40? No flow. Not the same. If I have here 30, right? I have here 40, and I have here, if you remember from last, what was the number here? 46, I think. Okay, 46 bar. Yeah, the static. Now let's say I have 30 bar. Okay. What will be the pressure here? Is it going to be lower than 46 or higher than 46? Lower, right? Because the density is a function of pressure. Okay? And if the pressure is lower, the density is also lower, and the hydrostatic column, which is the density of the gas times G times H, will be also lower. So here I might have, let's say, 33 or something. Okay? So that means my point will be down here. Okay? So the curve, and we know we're going to get a higher rate, right? Because we are using a lower pressure. So it's like the fluid is flowing against less restriction, okay, against less pressure. If you have a big pressure, the flow, it takes a lot of energy to flow against that pressure. If you have a slow pressure, then it can flow more easily. So the effect of lowering wellhead pressure okay, is something like that. So as the TPR, if wellhead pressure is lower, is reduced. If you see it has a similar shape than the red curve, okay, let's make it solid so that you can see it better. Okay, it has a similar shape, but the origin is different, okay, because the static pressure is different, and also you're getting more rate because the pressure is lower, so you're getting more rate than with the high wellhead pressure case. That clear?
You can explain again that one. We'll appreciate it.
Okay. Now we're saying the diameter change is clear, right?
Yes.
The curve is like a flower, has the same point, but it opens. Yes? It's these three curves here. Now, I'm asking what happens, I keep the same diameter as the red curve, but now I lower the separator pressure. Now it will be 30 instead of 40. Intuitively, you say what drives the fluid out of the formation is the difference between reservoir pressure and separator, right?
Yes.
If the difference is bigger, is more rate, right? I can have more rate. Okay, so you know that the intersection will be to the right of this point because I'm going to have higher rate, right? Now, to know how the curve will look like, I also say, well, I want to find the origin, okay? And so if I have 40 bar, the red curve, right, and I have no flow, maybe I will have here 46, okay? The density of the gas, let's say something like, I don't remember, yeah, let's say like 20 kilogram per cubic meter. I'm not sure exactly, I'm not sure about the number, but let's say it's 20 kilogram cubic meter. Now, when I go to the 30 case, the separator pressure is 30, right? Therefore, the wellhead pressure is also 30. How is the density of the gas going to be? Higher or lower than 20? The density of the gas. Huh? Yeah, let's see. Remember, the density of the gas is equal to RT over... No. No. It's P over RT. Yes? So assume that these don't change. Okay, if I have here 30 bar or I have here 40 bar, that means the density, if the pressure is reduced, the density is also reduced, right? If the density is reduced, that means that the hydrostatic is also going to be lower than in this case. Okay, so here instead of having 6 bar difference, now I will have maybe 3. Okay, therefore the point here, this one was 46 and this one now is 33. Okay, and just I join these 2 points. Okay, say I have to have more production and I have to have a lower origin, so I just join these 2 points and make a curve. And I'm telling you, because we haven't done it yet, but I'm telling you it has the same shape because it has the same diameter as the red. It has more or less the same shape. If you change the diameter, you change a bit the shape. Now, the next is, which is also a tough question. What happens if I increase wellhead pressure? Or increase separator pressure? What? The density will increase, right? Let's say now I have 50. Okay, now instead of 30, I have 50 here. The Q will be reduced, that's right, because I'm flowing against the higher pressure. Okay, so the intersection will be, let's say, here, someplace. Okay, and this origin will also be here. Okay, will also be bigger because you have a bigger pressure at the top, a bigger density, so you have even a bigger pressure at the bottom. Okay, so the curve for increasing wellhead pressure will be something like that. Okay, so that will be TPR for wellhead pressure increased. So remember, these are two effects. Diameter change, you change the curve over the same point. Okay, rotating it like that. Pressure change, wellhead pressure change is shifting the curve up and down. Okay, it's not pivoting through the same point anymore. It's shifting it up, moving up and down. The same shape, you will see, it will change a bit, but it has similar shape. Now there was one more thing we saw yesterday. Yes?
That point, intersection, is that the pressure at the intersection is the PWF.
That's, sorry, the pressure?
That intersects the IPR.
Uh-huh.
If we read, it's the PWF, this one.
This one, uh-huh. Yep. All of this here is PWF, okay? What we are plotting here.
And the index PWF.
Yep.
So, what is the desirable? Lower pressure to have
a higher QG.
Yeah. In theory, if we can get maximum rate as possible, that will be the best. Okay, but we discussed last class, there are a few things that we have to take into account. Okay. Now, what happens with if reservoir pressure goes down? Okay, with depletion. Remember, reservoir pressure in the IPR, if you remember in this equation, if I say that rate is equal to 0, okay, in the back pressure equation, QG CR PR squared PWF squared to the power of n. If I say QG is 0, that means that PWF is equal simply to PR. Yes? Okay, so this point here on the IPR, that's reservoir pressure. When reservoir pressure goes down, it's like the shape of the curve remains more or less the same because the C and N don't change much. Okay, so the shape is like you have a shifting, like a scale down effect. Okay, so like a shifting down. So with reduced reservoir pressure, the IPR also goes down. Okay, that's PR1, PR2. Okay, so the equilibrium point, if you are using the red curve, is also going to change due to depletion. So you have three complicated things in this plot, okay, and I decided to put all one on top of the other. Tubing diameter, wellhead pressure, and reservoir pressure. The three things affect the equilibrium. Okay? Any question? No? Clear? I wake you up. Yeah, I ask you, you tell me the intersection. What is it? Okay. So I want to now, let's go a bit away from the tubing because we're going to make another exercise later. So we know that to select the tubing, we want to maximize rate. Okay, tubing, diameter, selection. Okay, we want to maximize rate. That gives me US dollars, okay, or good benefit. But at the same time, I want to minimize cost. Okay, a high diameter is also very costly. Okay, so I have an issue there. Also, it has to fit the production casing. Another thing which is very important is the depends on the tubing hanger. Okay, and the thing is that in this tubing hanger, if you have too many holes, it has to have just the holding. Okay, it's holding the whole weight of the tubing. So if you put too many holes, it doesn't have enough. It's not structurally strong to hold all of that tubing because of all of so many holes. So that's why the sizes that can restrict the size of the tubing that you can use. Okay, so that's structural limitations and space. Okay, you might have here a line, if you remember, is for the subsurface safety valve. Another line is for the pressure transducer. Okay, if you have a pump, another line might be for the pump, for the ESP. Another line, if you're making some sort of injection, okay, you can have a chemical that you're injecting. all kind of things. And then that limits the space you have for the tubing. And there are two more things that we are going to cover later, okay, today. And one of them is called erosion. Okay, the velocity of the gas has to be less or equal than the erosional velocity. Okay, to avoid that I will start to take out material from the walls of the tubing. And there is one more thing, which is liquid loading in gas wells. Okay, and also we have something similar in oil wells called slugging. Okay, that the velocity of the gas has to be greater or equal than a loading velocity. And that we're going to discuss a bit today. Okay, so these two we're going to discuss, I guess, after the break. But just keep them, because after that we're going to make the exercise. But let's now talk about the flow line. Okay, yesterday we were discussing about flow line. Okay, flow line sizing considerations. Okay, how do I define the diameter of my flow line? And here is very similar to the tubing, right? So I want to maximize rate. Okay, that's the first thing. I also want to minimize cost. Okay, a bigger pipeline will be more difficult to manage, will be more difficult to lay will more expensive to transport. It will take more time to lay on the seabed or on whatever you're laying your pipeline. So remember, maximize QG is usually minimize delta P. Okay, also here is minimize delta P. Now there are a few things we have to be careful with flow line. Okay, because in the well really the tubing is restricted by the casing. Okay, so we can go up to a certain limit and we cannot go above that. When we go outside, really we can use any size we want virtually, okay, depending on the rate. But there are a few things we have to be careful. Okay, one of them is liquid transportation. Okay, so for many lines, like I mentioned, we not only have gas flowing through the pipe, okay, but we also have some liquid. And we will see about the sources of this liquid a bit later this week. But this liquid can be condensate or can be simply water. Okay, water that comes just like in the air that surrounds us when it gets cold. Okay, you have condensation of water, or it can be condensate, which is basically a light oil that is condensing from the gas. Okay, and every time, so the velocity of the gas has to be enough to be able to drag these liquids. Okay, to drag it and to take it further to where you have the end of the line when you have a separator or whatever is that you have. Now the problem, sometimes the velocity is not enough, okay, and then the liquid starts to accumulate in the lower parts of the pipe. Okay, and there are a few issues associated with that. Okay, one of the issues, if you have water accumulation, that can cause corrosion. Okay, if it's water, you might have starting corrosion, and then at the end you're going to have a leakage. Another issue you can have is a pipe blockage. Okay. That means if, for example, you have a very pronounced declining section, the liquid level can go all the way here, and then you have blockage. Okay, and then you have is impediment for the flow. Or you can also have slugging. Have you ever heard the term before, slugging? Yes? Okay. In that case, if you have a blockage, usually when you have a blockage, you have significant amount of liquid accumulated in the pipe. That pressure here starts to build up because the gas cannot flow anymore through that elbow. But the well is still producing, it's pushing that gas from behind. So that pressure will start to go up in time, okay, when you have that's time, start to go up and up and up until that pressure is enough to overcome the hydrostatic height. And it just flush the whole liquid out of that low point, okay? So if you see here at the separator, okay, let's say here now we are at the end of the separator, okay, you see the amount of liquid with time, you see that you have very little liquid. And then when that plug comes, whoosh, you have suddenly a very high amount of liquid, okay, until that pass and then goes back to no gas. Okay, so that's what I know as logging. It's like a sequential flow of liquid and gas with liquid, liquid, batches of liquid, batches of gas with liquid. And that's a problem. And that's a problem because if you remember, we had our separator, and the way we are controlling that separator is basically with these two valves, right? We have the valve on the liquid and the valve on the gas, and we have this controller, this level controller, and this controller. Yes? Now, sometimes that liquid can be so huge, okay? The size, the volume of that liquid that I have here can be so huge that it's even much bigger than the volume of the separator. So what do you think will happen if I receive all at once that block of liquid? No matter if I put here fully open valves, okay, it won't manage to keep the pressure constant. You will have liquid coming into the gas line, liquid coming everywhere in the system. And then I have a batch of gas, it does the same effect. The liquid goes very low and you have gas in the liquid line, a catastrophe, okay, a disaster. So in those cases, I don't want really to have slugging. Okay, I want that the liquid, the gas velocity will be enough to take out continuously and avoid accumulation of liquid. Okay. Just to call to your attention, so if slugging is unavoidable, okay, a device called a slug catcher is sometimes used instead of a separator. A slug catcher is sometimes used okay. And the slug catcher, basically I have my main line coming from the flow line, and then I have a header, okay, a big pipe, and then I have a lot of long pipes, okay, that they distribute where the liquid and gas is distributed. Okay, and after all of them, I have a drainage that will collect all the liquid, and one that will collect all the gas. So let me maybe put it here at the end. Okay, the gas will go up. Okay, and in this case, let's make the liquid level Okay, and you can have many of these branches. The idea is that you increase dramatically that volume, such that the volume of all the pipes collected one next to the other is much bigger than the volume of this slug, of the longest liquid slug that you can get. Okay? Of course, it's much bigger, you need much more space, it's much more expensive, the control, how to connect all of these branches, but that's the only way we can deal with slugging. Okay, so slugging, a big issue. If you have gas and you're expecting some liquid, be careful with the size of the flow line. Okay, you have to be sure that you have enough velocity to lift it out. There is one more thing. Okay, so many things we have to take into account, but there is one more thing with it, which is hydrate formation, especially for gas. For gas. Any of you know? Do you know what hydrate is? No? Okay. So that happens if, yeah, so so hydrates, let's make a short, not make it very long, okay? Do you prefer to take a break now? Or this? Okay. Okay, hydrates. Okay, very, so it's called actually natural gas hydrates. Okay. And you know that water, the molecule of water, right, it doesn't like, even though it's oxygen and hydrogen together, they don't like to be too close, right? You have some polar, I talk about chemistry, you start closing your eyes. Just, I do the same, so I understand you, but it's going to be short chemistry, no problem, okay? So remember, this molecule is arranging itself because oxygen has 2 extra electrons, right? So it's arranging itself such that it creates like some sort of a dipole. Okay? It has negative charge here and 2 positive charge here. Because of that uniqueness, it can come and pair up with another oxygen that I have here, right? And can form this sort of, how do we call it? This hydrogen bonding. Okay, they don't exactly become one compound, but they have some affinity and they start to form some sort of a structure between all water molecules. When the temperature goes down, okay, actually it becomes a solid. Okay, that becomes like a cage, and let me show you how it arranges itself when it becomes very cold. Okay, it's like you get very cold, you try to get very close to each other and everything very compact, just to keep everything, okay, just to keep the heat inside. And it forms something like that. Okay? It forms some sort of a cage. Okay, when temperature drops. Goes down, okay, it forms a solid structure that is like a cage. And you see here, that's the oxygen, and those are the hydrogens. And they, due to that formation they had from before, they connect to a nitrogen from another molecule, and they make this cage, which is a very nice house. Okay, and then there come some small molecules. I think they are in the order of 9, if I'm not mistaken, 9 Armstrong. Okay, and remember, an Armstrong is 10 to the minus 10 meters, okay? Very small molecules, and they see a house. Say, let's go inside this house, and let's live in this house forever. Nobody's going to take me away from this house, okay? And these molecules are typically methane, ethane, sometimes you have, yeah, you even might have propane. Sorry, this should be H6. Yeah, you have CO2 and also nitrogen. Okay, all of the small molecules, they can go from the gas, they can go and they can start living on that house. Okay? The problem is that that substance is a solid. Okay, so it looks like ice, pretty much like ice. It looks like that. Okay, so that can form, that's a solid block of ice that can form on the pipe when you have that reduction in temperature. And what happens at the end? Builds up, builds up, builds up, and just blocks the pipe. Okay, and then you have no production anymore. Okay, so you need to have the following conditions for that to happen. Okay, which we have to be very careful. So you have to have small hydrocarbon molecules. Okay, that means that you have to have some sort of gas, C2H6 or C3H8. Okay, you have to have free water. The water has to be liquid and has to be out. It cannot be just evaporated in the gas. You have to have free water, okay, liquid. And the next condition is low temperature and relatively high pressure. Okay, and here temperatures, we're talking about 4 degrees Celsius, for example, for 12 bar. But the curve actually looks something like that. So here I have pressure, here I have temperature, and it does something like that, very sharp. Every combination of pressure and temperature that is to the left, that is in this area, you will form hydrate. Okay, and every combination on this area, no hydrate. Okay, so that point that I'm giving you, 4 and 12, is just here, okay, 4 and 12. But if you're working for higher pressures, you will have, of course, higher temperatures, okay, at which the hydrates can occur. So why am I, raising up this issue about hydrates? Because if I choose a very big pipeline, let's say I'm laying a pipeline someplace where it's cold, okay, maybe not in Mozambique, but subsea, okay, the temperature subsea, they can be close to 10 degrees, so they are close sometimes to the hydrate formation temperature, okay, and, okay, so we can plot, okay, if we have our flow line, okay, let's say, we have our flow line, we have our temperature along the flow line, okay, and we know the temperature is going down, okay, that will be, let's say, wellhead and going down, and you also have the pressure, which is following a similar trend, okay, wellhead pressure and then going down towards the end of the flow line. If you plot now every pair of points, okay, for each position, every pressure and temperature, you plot it in this diagram, it's going to show something like that. Let me use another color. Okay, that will be P, let's say, into the flow line, P into the flow line, and it will go out like that. Okay, P out and T out, where pressure, both pressure and temperatures, are reduced along the flow line. Okay, as I'm flowing. So how the pressure drops, if you remember from your course in heat transfer maybe a long time ago, okay? What affects the drop in temperature in the pipe? If you remember, was if I look at a section of pipe, right? Okay, I have something that is called this Q, this heat that is leaving the pipe. And this Q is equal to the area, right, the surface area, times a coefficient that we call U, the heat transfer coefficient, and the difference between the wall, the temperature at the wall, minus the temperature of the ambient, right? You remember that? Okay. So some things I cannot control, right? Like I can put some insulation in the pipe. It can be very well insulated. I can have some marine currents that are cooling my pipe. The difference, I will always have that difference. Initially will be very high, okay? But one thing that I can control is the area of the pipe. If I make my pipe smaller, this area will be smaller and Q will be smaller. So I will be losing less heat to the environment. So the cooling will be, so let's see, let's paint it something like, let's make another line. Sorry if, I hope I'm not, okay. So if you use, for example, a small pipe, a small diameter, the area will be small and then Q will be also small. And then I will be a bit outside of the hydrate region. Now if I use a big pipe, okay, then I will have a lot of heat transfer, and then I might end up inside the hydrate formation region. Okay, so that's big diameter, big area, and then big heat, and then I might end up in the hydrate formation line. Okay, so yeah, just to be aware of flow line, we have a few more things that we have to take into account. Okay, so one of the things is not only to maximize Q, minimize pressure drop, the cost is very important, but the liquid. Okay, also when you have oil, you have the same phenomena. You have like plugs of liquid and gas that we should avoid. This in general is called flow assurance. Aseguramiento de flujo. Okay, and it consists in ensuring the uninterrupted flow of hydrocarbons from reservoir to the processing facilities. And it's a position inside the company. You see some positions they have flow assurance engineer. And it's to deal with all transportation problems that can cause that my flow will stop. One of these problems is hydrate. Okay? There are many more. Slugging is also a problem. Corrosion is also another problem. Sand accumulation. You have many problems within flow assurance. Okay? So due to flow assurance considerations, sometimes that can affect also the diameter of the pipe, which pipe to choose. Okay? And in this case, it's extremely important to know, first to know how the pressure and temperature are going to change in the pipe. We already know how to do pressure. Temperature, I haven't told you that yet how to do it. And see if it's going to fall inside or not of this zone. If it's going to fall, then I have to make something. I have to isolate the pipe, or I have to do something. This will change depending on the composition, okay, of what kind of hydrocarbon you have. Okay, so it will change if you have one field which has some heavy components. It will look different. So it will look different depending of the composition. Okay. Now, one more thing before we take a break. Sometimes I cannot avoid that. Okay. If I make the calculation and no matter what I do, I change insulation, I reduce diameter, I do everything, I still go inside the hydrate zone. Okay, so in that case, I use a method. So let's write here, when the hydrate zone cannot be avoid it, then I use something called hydrate inhibitor. Okay, you maybe heard of it before. And one of them is, for example, methanol, okay, which is a molecule, okay, that again has oxygen, okay, in it. So due to the oxygen, it tends to separate and tends to have a negative charge and a positive charge here. Oxygen is always very greedy with electrons, okay, it likes to keep electrons by itself. So by doing that, if you remember the other molecule that I have here, plus and plus, this minus will tend to disassociate and block this plus, okay? OH will tend to be here, and this C will tend to be here. And then you don't have the formation of this cage anymore, okay? Or it will take more effort to have the formation of that cage. And the way the line is changing is you inject some inhibitor, okay, P and T. The original line might be like that, and then when you add the inhibitor, okay, you just move to the left. Okay, so that's without inhibitor, and this is with. Okay, and if you add the amount of inhibitor that you're adding, usually is in weight percent. Okay, so usually typical numbers are 0.4 to, sorry, not percent, but yeah, so it's 40% up to 60% on the water. Okay, so that means the mass flow of the inhibitor divided by the mass flow of the inhibitor plus the mass flow of the water, that is a number between 0.4 and 0.6. Okay, it's within that range. That means if I'm producing 1,000 barrels of water, I have to add how much? 1,000 barrels of inhibitor, right? If we say 50-50. So that's a lot of inhibitor that we have to add. Okay, if I'm producing 1 barrel, my life is fine. I'm happy. If I'm producing 1,000, I have to inject quite a lot of barrels per day to be able that my line is here, and in the expansion in the pipeline from P in, T in, or P out, T out, I don't reach the hydrate zone, okay? Because I cannot have these flows, they happen in the pipe, and then to remove them is a big problem. It's a big operation. You have to bring the, you know, a lot of experts. Is that clear? Yes? Okay, let's take a break. Let's say 20 minutes. Okay, and we come back for the second part. It's not so simple as to just increase rate and that's all. Okay, reduce pressure drop. There are a bunch of all other things we have to take into account. Flow assurance is a big part of it. I hope last year we did an exercise on wax. Okay, for it's a bit easier to calculate temperature drop in liquid than in gas. So probably this year we're going to repeat that exercise. But the bottom line is that to calculate this line is very important. Okay, it's very critical. And for that you need to know the equation, why, how do you compute, and that depends pretty much on this U, but depends also on the properties of the fluid. Okay, so now let's go back to the tubing side. Okay, and for that that's going to give the ground for our next exercise. Okay, and we're going to look at two things. So we're going to go back to the tubing. We still have some things to do there. So one of them is erosion. Okay, and as I mentioned, erosion, there is a standard called 14E API. API is the Association American Petroleum Institution. And this standard, it gives you the it gives you, it says that the velocity of the gas, okay, that you have of the fluid, okay, it says the velocity of the, basically the fluid that you have, it should be less or equal than a constant, okay, called C divided by the square root of the density of the mixture. And that C is typically 100, 120, depending how conservative you want to be. And the density of the mixture, if you have a mixture, okay, if you don't have only gas or only liquid, if you have a mixture, should include solids. Okay. If you have sand production, for example, that's going to change your density. Okay, the sand is typically given in concentration, ppm. Okay, you have so many ppms of sand, 1,000, 2,000, and you have to use that to compute the density. And so I ask you, the velocity where? Where should I check that criteria? If you remember, we did an exercise already, right? We have wellhead, or we have a pressure, and then we have, so if we plot, let's plot here the pressure, how it will look like, versus TVD. How does it look like? It looks something like that, right? It's just decreasing until I reach P wellhead. Okay, and this is PWF. Now, how is the local rate, or first the standard conditions rate, how is that going to behave? Q standard conditions, Q gas. That's just going to be constant, right? Because that's like mass flow. We already said mass flow set by the production, by the reservoir, by the petroleum engineer. Okay, that's just constant. Now the local, so let's put that in blue, I think. Blue. Okay, pressure, rate. So how does the local rate behave? What is the definition of the local rate, if you remember? QG equal to QG, this is at standard conditions, times BG, right? And BG depends on pressure and temperature. And if you remember, what is the behavior of BG with pressure? Is something like that, right? So it's a number that is smaller than 1 and is usually something between 0.1 and 0.01. Okay? It's a number very small. But that tells you that the rate, how should it go with depth, or how should it go with pressure? Here the pressure is low, therefore the rate should be okay, let's say this pressure is bottom hole pressure and this pressure is wellhead pressure. The rate is increasing, right? The local rate will this one is constant, right? So if we plot now on the same plot to make things messy, it will go something like that, right? QG local. Okay. And now how do I calculate the velocity of the gas? Is the local rate divided by the area of the pipe, right? VG will be QG, and that will be P phi squared for QG, right? Okay. So where should I check erosion, the erosion criteria? What is going to be the most critical point in the tubing? Where is VG going to be maximum? The velocity of the gas. Huh? At the wellhead, exactly. So usually, for erosion, sometimes it's just simply go and verify that you don't have erosion at wellhead conditions. Okay, so sometimes it's very simple. Some things about the units of this equation. This equation, you have to use it in the units that you like, field units, and that will give you in feet per second, and this should be given in pound per cubic feet. Okay, just to be aware, if you're going to use that equation like that, you have to use it in with field units. Okay. Now there was another thing we had to take into account that was liquid loading. Okay, liquid loading. Okay. And if you remember our discussion yesterday, we have our tubing, and we have some gas flowing through the perforations, and the gas is flowing up. However, due to some reason, maybe some liquid is coming with the gas, okay, maybe something is condensing, you start having some droplets of liquid, okay, of condensate or of water with the gas. And when the velocity of the gas is not enough to drag the liquid up, okay, then you will have that the liquid will start to accumulate, okay, and will start to create a back pressure. Okay, and this it will be an additional back pressure that you're going to have acting on the reservoir. Okay, here I have to put it like that. Okay, you have accumulation, the gas is not able to evacuate that liquid that is being produced and is going to start to accumulate on the well. Okay, to look at that, I'm going to cover relatively quickly a criteria, so a liquid loading criteria. Okay, and that criteria was an engineer called Turner. I don't remember for which company was he working, but I think it was around the 50s maybe. I think 56. Well, I don't remember. But actually he said, well, if we look at the droplet, right? Just a droplet, that's a droplet of liquid. The droplet will have acting on it a few forces, right? So one of them is the force of drag caused by, the gas flowing around it, okay? It's like when you take your hand out of the window in the car and then you feel some resistance pulling you out, is that force. Then other forces that it has the mass of the droplet times gravity. Okay? And there is another force that he took into account, which is buoyancy, right? When you have solid submerged, remember in this case it's submerged in a gas, okay? So it has some buoyancy. And maybe here is not so relevant, right? When you have low pressure. In that case, the density of the gas is very low. It's like 1, okay, like what we have here now in the air. So it's not very important. But down here, the density can be 200, okay, it can be very high. Actually, maybe a third of the density of the liquid. So it's important to take that into account. So that will be F buoyancy, okay, going up. So then he made a force balance between them. He said, well, if I say drag plus buoyancy, that should be equal to weight, okay, weight of my droplet. And then he was expressing each one of them separately. So here I have the volume, I think he put the volume of the droplet times the density of the liquid times G. And what is that force going up? Is again the volume of the droplet, but the density of the gas times G, right? And then I have the drag force, which is density of the gas, CD velocity of the gas squared. Okay, and the area, of course, of the droplet. I have to put it a bit down. Okay, CD velocity squared, the area, okay, and the area of the droplet, okay, which is will be just a circle. Okay, the volume of the sphere is over 6, right? The volume of D, and then the area of D is simply pi over 4. Okay. So that would be, if I make, they are normally not equal, right? They are normally, the droplet is going up. So normally they are not exactly equal, but they will be equal just at the point where the droplet is not going up or not going down. It's just staying there. Okay? So that's exactly the critical, the definition of this B. Here I have to, this is volume, but this velocity of the gas, this is the critical gas velocity. Okay? When exactly those forces are exactly the same. The drag force going up and the buoyancy going up and then the weight going down. Okay, so then I can do some algebra, okay, to start grouping. So I say pi feet to the 6. Then I do density of the liquid minus the density of the gas times G. Then I divide by, so I have here the velocity of the gas. I multiply times 2, divide density of the gas by CD, and the area of the gas is P over 4, and I take the square root of that. Okay? This is the drag coefficient, okay? Okay, it's just a coefficient that I measure what is the, so if I express this force, the drag force, with that expression, okay, drag okay, so I measure all the rest, okay, measure the density of the fluid, I measure the velocity of the sphere, of the gas, I measure the area, then I can find a correlation for that drag coefficient, okay, and that's usually available for spheres, okay, that's, some people did some work long time ago. Okay, so it's like a drag. If you see, it's a ratio. If you see the definition, CD is a ratio between a force, a drag force, and density and kinetic energy. Yes. Okay. It's a dimensional number saying a ratio between a force and a kinetic energy. Okay. But we are not going to go too much into that. Just saying that that force, you can express it for a sphere, assuming that it's exactly a sphere, you can express it like that. And actually, because the velocity of the gas is also very high, you can say this is going to be a constant, 0.44. because you are in the turbulent regime. Okay, if you plot this CD, okay, versus the Reynolds number, it has a behavior similar to the friction factor. Okay, first is high and then it starts and then becomes low, and this number here is 0.44. So we assume turbulent regime, that's 44. This 2 goes with this 6, this diameter goes with this diameter, pi goes out here, and then at the end we end up with this expression. Yeah, 0.44. Okay. Now we have a big problem here. Okay, something that is a very big unknown. Density of the liquid, density of the gas. That's something that we can, if we have the pressure, right? We are discussing this case now. Okay, we have the pressure in our well, so we can calculate the density using the real equation of state, right? Density in that case can come from simply the density of the gas. It's fine, it will change with pressure. Okay, but you can say that the density is equal to pressure divided by RT, right? The density of the gas. No problem. Density of the liquid doesn't change much, right, with pressure. So you can more or less always assume a constant number. This one I have, this one is 0.44, so I'm almost ready. The only thing that is missing is the diameter of the droplet. What diameter of the droplet to use? So that was a big question. Okay, what kind of diameter I will use? Some people say, well, if I have a lot of liquid, I will have bigger droplet. If I have a little bit of liquid, I have a smaller droplet. But there was a researcher called, I think he was in the Netherlands, called Himse. Okay, that he said, well, the maximum diameter of the droplet. Okay, he did some measurements in the lab, and he said the maximum diameter of the droplet, okay, that I call D max, can be related to a special number, okay, a number that is called the Weber number. Okay, I can make exactly a relationship, and I say that Weber number is the density of the gas, the velocity of the gas, the diameter divided by of the droplet divided by the interfacial tension, okay, this sigma. And he could make a correlation. He said the maximum number will occur when this Weber number is equal exactly to 30. For all of my experiments, always when this combination of parameters gives me 30, that's when I had my maximum diameter. Okay, and then we have almost everything we need, right? We have the density we can calculate, the interfacial tension, that's something we will talk a bit later, but you can calculate that, okay? The velocity is the same velocity that I was using here, and that will be the D max. Okay, so that means if that balance is honored for the biggest droplet, I'm sure it will be honored also for the small droplets. Okay, we'll be able to lift also the small droplets. So I do it for the worst case, which is when the diameter of my droplet is maximum. Okay, that's phi maximum. Okay, and then I substitute, let's call this equation 2 and this equation 1. So then I substitute equation 2 in 1, okay, and then I end up with the famous critical velocity for liquid loading that looks something like that. Sigma, sorry. And that's something we are going to use in our exercise now, just to verify that. 0.25 density of liquid. Okay, if you substitute one equation, it gives you that, and that will give you in meters per second, and the density has to be in kilogram per cubic meter, and the surface tension has to be in Newton per meter. Okay, so I have to verify in every location in the pipe that the velocity of the gas has to be greater or equal than the critical velocity for loading. Okay? So that's what we call the Turner criteria for liquid loading. Okay, that the velocity of the gas has to be greater than that critical velocity, just to be able to lift the liquids. So I think now we have everything we need for our exercise. Okay?
If this criteria is not verified, then we would face that phenomenon that you explained.
You will have to have liquid accumulation, and then you will eventually will build up on the well, and then it will kill the well. Okay? You will have just too much back pressure. It's like basically the gas cannot, yeah, this one here. Okay. So this one came from a report, completely empirical. They did some measurements and they found this factor, erosion factor. Some people say it's too conservative, that they should lower the number, increase the number. And this one came from purely force balance. And some people, some software, they say, well, if we change this number here, we can tune it and match the data we have in the field, because we know it doesn't work 100% correct. Okay, and that's sometimes because when we are looking at the tubing, we're basically assuming that all the liquid is transported in droplets. Okay, and in reality, that's not the case. In reality, you have that part of the liquid is at the walls. Okay, sticking to the walls. So Turner, he made his criteria based on the droplets, but they say actually you can also have that the field is just slipping down. Okay, it's slipping down. So there are a bunch of other people trying to improve. Turner saying, well, we can change that number, or we can now use a criteria based on film instead of droplet. That is too advanced for this course, so we are going to use just this equation. Okay, so now let's go to the exercise. This exercise, you won't have to deliver, but it's a class exercise. So it's what we call pressure traverse calculation. In the tubing. Okay, so far we have calculated pressure either at the discharge of the tubing or also at the inlet of the tubing. Okay, but to make this calculation, like to verify erosion, verify liquid loading, sometimes we're interested to see how pressure, how velocity, how rate changes along the tubing. Okay, for all kind of reasons. We are interested to see what happens with pressure, rate, velocity, maybe properties, density along the tubing. Okay, and that I call pressure traverse. Okay, and the way we are going to do that, so how can I use the tubing equation that we used last class to make a pressure traverse calculation? How do you think? Remember, before we had our tubing like that, we say PWF, that's P wellhead, and we just calculated either this one or this one, period. Don't calculate anything in between. Okay? Now, what we want to calculate is actually, well, in different positions in the tubing. I want to calculate for all of these from I equal 1 to I equal n. I want to calculate all properties. So can I use the same equation that I was using before? The tubing equation? If you remember, that equation was, let's just refresh your memory. Okay, can I use that equation? Almost. Okay, we cannot use the equation just like that. Okay, but if we say we create a CT for each segment and an S for each segment, right? It should work. I make one equation for this segment, then I make another equation for that segment, and then I make another equation, and it should work, right? It's just I'm splitting the tubing in many small tubings. And now I'm finding for each one of these segments a CT and an S. Okay, so for this case, for this well that we are analyzing, I think the wellhead pressure is fixed. Okay, and the rate is given. Okay, the rate I think is given. So we have, so how do we use the equation in this case? Okay, I calculate CT and S for each segment. Okay, and now how do I start my calculations? For the first equation, I cannot start from here, right? I don't have the pressure here. So I have to start from the top. I have P2 and I calculate P1. That will give me this point. And then after that, I use that will be my P2 to calculate my new P1. Okay? Now I say P2, I calculate P1 and so forth. Okay, so I have to go from top to bottom. Okay? If for some reason I had the pressure here, then I have to do the opposite. I have P1, calculate P2. Now I have P1. Now this becomes the inlet to the next segment. Okay, if we look at this like a segment. Okay, now you have the inlet P1, that will be P2. Now you look at the other segment, this will be P1. You want to calculate P2, and so forth. Okay. So let's do the exercise. Let's see if we have time. Hopefully we have time. Okay, so you have to go to my website. The exercise is there. It should be in a folder called class exercise. And it's the one that says pressure traverse dry gas well. Okay, so you should have this screen. Okay, so we have, is the same, I think it's the same well, okay, that we were looking before, is this EVA well. We say that it's a tubing of 2.8 kilometers down, okay, it's a vertical well, because MD, measured depth, is the same as TVD, so it's a vertical well. And we have several positions in the tubing where we want to find the pressure. Okay, we want to calculate now only at the outlet or inlet. We want to find along the pipe. Okay, the temperature has been measured from, or I'm making here an interpolation, I think, from reservoir to wellhead pressure. Wellhead pressure is around 70 something. No, 90. Okay, 90, and reservoir temperature is 100. So you have 10 degrees loss, temperature loss in. So if you remember, to calculate CT, we need a bunch of things, right? We need friction factor, we need a few things, but we need, one of the things we need is the average temperature, the average deviation factor, and the average pressure, right, on that segment. If you remember from a few classes back, let's see if I have it here. Okay, if you remember the definition of CT, it was this one. Okay, so you had the angle, the inclination angle, you had the diameter of the tubing, you had the friction factor, and you have the average set and average T. Okay, so to find CT and S, if you remember the definition of S is here. Okay, so you need also the average set and T and the length. So I suggest first we calculate the average temperature. Okay, but it has to be, remember now, there will be an S and a CT for each segment. So we need the average temperature of that segment. So how do I calculate that? The T average will be simply this number, the end of the segment, and the beginning of the segment, okay, divided by 2. And calculating the average temperature of the segment, 0.5. Yes, average temperature, the temperature at the beginning of the segment, the temperature at the end of the segment, and then I make an average. And remember, if I have, how many points I have here? I have 11 points, 10 points, 11 points. I will have 10 segments because segment can only exist between 2 points. Now, to calculate the set, okay, the average deviation factor, I need to have also an average pressure. Okay, and the average pressure, that's what we're going to calculate. That's what we don't know. Okay, but we said yesterday, well, it shouldn't matter much. Okay, the average pressure. So we know the pressure at the wellhead is here. Okay, is 40 because it's very close to the separator. So that would be 40. And if you remember from our flow equilibrium, what was the downhole pressure that we found from yesterday? Was 88, right? Something like that. So let's use, so how many, if we go, so that will be every 200 meters, how much will that be? 5. So to get here to 88, right? We want to get here exactly to 88. So how many, what is the step we have to use? It will be 48 divided by 3,000. So that's how much? Okay, that's about 3 degrees every 300 meters. So let's see if the calculation, I made it correct. Okay, plus 3, and then I drag it down. It's not, so maybe 6. Final calculation. 88. Okay, 4.83. Yes, okay. From the top of your head, okay? We say, because we already did trap, okay? We did some cheating. We solved this exercise yesterday. So we know what the pressure at the bottom has to be, okay? And I just say, well, I have to go from 40 to 88. I will just assume it's a linear, okay? It's just uniform. I have the same increase every depth, which is not correct. It's an assumption. But later I'm going to see how bad my assumption was. Okay, so you can use any number. Actually, I'm going to change here. I know even is 483. Let me put just let me just use 5. Okay, so I'm going to use increments of 5 all the way to the end. Now I can do the same. I can calculate the pressure average. That will be this pressure plus this pressure multiplied or divided by 2. Okay. And remember, for that doesn't exist. A segment is just between 2 points. Okay. Now I need to calculate the average deviation factor. That deviation factor will use this pressure and this temperature. And if you remember the name of the function, what was it? C factor standing from yesterday. The C, see? The line is just an average, just like the temperature. I'm making an average between the upper point and the lower point. Okay, and then I drag it, average of this point with that point. Okay? C factor, so I find for the function to calculate the deviation factor, which is C factor standing, the pressure of that segment, the average pressure, the average temperature of that segment, okay, and I have to be careful with the units, is bar and Kelvin. The specific gravity of the gas is someplace here, and that I have to block. And the unit will be 2, okay, because I'm using metric units. Okay, S is here, okay, and S requires the specific gravity of the gas, which I have it here in B6. You have to find a user-defined function called S, and then I block it. T average, that should be in Kelvin. I take the T average of that segment, and that I don't block because that is going to be different for each segment. Set average, this guy here, the H, what was the H, if you remember? H was the difference in height of the segment. So it's just simply the TVD. So it's going to be basically this number minus this number. Okay, the elevation of the segment, the difference in height of the segment. Okay, so specific gravity of the gas, average temperature of the segment, average deviation factor of the segment, and the not the length but the elevation of the segment, the height of the segment. Okay, and I'm getting a number 0.29. What number did we have yesterday, if you remember? I think it was 0.3. Okay, I think so. And then I drag it down for all the segments that I have. let's find the function. It's called CT. I think it's called C flow constant, I think. Yeah. Okay, and that's using the diameter. That should be in meters. The diameter is tubing ID here, B3, and I have to block it. The specific gravity of the gas, that will be in B6, and that also I have to block. The friction factor, that, remember, for gas depends only on the diameter. So I have it here, then block it. C average, this guy, I don't block it. It will be different for each segment. T average, C15, L, that's what? That's the length of the segment. Okay, in this case it's vertical, so the length is equal to the height of the segment. Okay, so it will be simply the TBD from the previous minus the previous. Okay, and S is this S factor here. Okay, and I got 1.3 to the power of 5. Okay, and you see there is some variation on this CT depending on the segment. The upper CT has a larger, the upper segment has a larger CT than the lower, Okay, are you getting similar numbers? Yeah. Now let's calculate the pressure. Okay, that's almost the last step we have to take. Okay, the pressure. So how do I calculate? I start from a pressure that I know, right? Which is, yes? Coming. We start from wellhead pressure, constant.
Can you go up?
Okay. No? Not yet? Okay? Okay. So we have to start from the point that we know the pressure. Okay? We know the pressure at the wellhead. That's what we are keeping fixed. And we are moving down to the pressure that we don't know. So we have to use the tubing equation, right? We have P2 and we have to find P1. Okay? So let's use here P1. Okay, the equation is called tubing P1. Tubing P1. First, we have to take the CT, and be careful. Here I have to use the CT from the segment, which is the first segment. I have to use the S also of that segment. Now each segment will have their own CT, and I cannot block it. I have to drag it, and it will use the CT of the segment that it has to take. P2 is the pressure at the discharge, will be this one. Okay, and that also I don't have to block, because when I drag it down, I want to use of the previous segment. Okay, the inlet pressure to the previous segment, and the rate is going to be constant for all of them, right? Is the same rate. You have one segment after the other, but all of them will have the same rate. So that will be this QG, and that I have to block. Okay, so you see, instead of having, from 40 in that segment of 284 meters, I have 6.45 bar. Okay, and then I drag it down, and I should get something like that. Okay, so I'm going to keep it here if someone needs this.
One question.
Yes?
If it was, if we were calculating in the, like the exercise of yesterday, where the 2G rise, it wouldn't be constant here.
No, but this is the standard rate. Okay, so this is like mass flow. So that will be constant for all segments. Okay, now we're going to calculate the Q in every segment. Okay, the QG.
QG, okay.
Yeah. Did you get similar numbers?
Yes.
Yeah? So I think it will be populated automatically, okay, this plot. If you see, it's not exactly linear, it has some curvature, okay? It's very close to linear, but it has some curvature, okay? So if you see here the numbers that I assumed from 40 to 90, they are close, but not exactly the same that these numbers. So just to improve my calculation, I can just, and be careful with this step, I copy this column, okay, I copy, and then I paste on my assumption. I'm going to improve my assumption, but I can paste, and I have to paste values only. Be careful, I don't want to paste a formula, I want to paste values. okay? And you see that change now the CT, okay, slightly, but the numbers now are very close, okay? Now in the difference is 0.1 bar from what I assume and what I calculate. I think that's good enough. I think we can leave it like that. Okay? But if you need, you might need different iterations of copy and paste. Okay, you obtain a number, you see that they are still different, you paste again and you paste again until they are very close. Okay, now we have pressure along the tubing, that's what we wanted. And now we have to calculate the velocity of the gas in different places in the tubing. For the velocity of the gas, we need the local rate. For the local rate, we need the BG, and for the BG, we need the deviation factor. Okay, that's what we have done yesterday. Yesterday, I think, was it yesterday or I think it was on this day? Yeah, if you remember, we had pressure, temperature, then we need the set, right? Then with the set we calculate BG, and then with BG we calculate the rate, and then we calculated the velocity of the gas. So now we're actually like repeating this exercise, but now we know where this P came from. Okay, we are not just we know where it came from. So let's do that. Let's calculate the set. That will be again the same function, C factor standing. Okay, here we're going to use the actual pressure of that point, the temperature of that point. Okay, here I should use let's use it here. The pressure of that point, the temperature of that point, not of the segment. Okay, now we're calculating at that point, at that particular depth. The specific gravity, and that I have to block with F4, and the unit will be 2. Then I drag it down.
Yes. Teacher, sorry, professor.
Yep.
At the end, could you, at the end, explain again when we use the average and when we don't use the average?
Okay. Yep. Here there is something that is a bit wrong here. We made a mistake. I think if you go back to Alt F11, okay, you will see that the unit of temperature should be Celsius, and we are using Kelvin. Okay, so we have a small mistake there. So let's see, where did we used it here, right? And this said we should actually use T in Celsius, which is that temperature minus 273.15. Okay? Because the inlet of that function has to be in Celsius. And now it changed. Okay? And the same thing for this set. I have to take the temperature. Okay, a small mistake, doesn't change much the results, but in reality, this C factor standing function, it takes the temperature in Celsius. So the change that I made in this column, F, I changed, instead of taking C15, you have to subtract 273.15, okay, to take it from Kelvin to Celsius. Okay, and then I have to drag it down once more.
And do the same in the G1.
And also the same thing here with this set. Okay. Now the question that they had here: what is a segment and what is what is a point? When do I want to make calculations on a segment and when on a point? Okay. The segment is when I want to calculate CT and S, right? Because CT and S, they cannot be assigned to a point. They have to be assigned to a piece of pipe. Okay. So for that, this S and CT, they need an average set and an average temperature. When they were asking here in the front, okay, when do I use point? I make calculations in a point, and when do I do on a segment? Okay, so I'm saying that we need CT and S. They are defined for a piece of pipe, okay, for a piece of segment. They are not defined for a point. And to calculate the CT and the S, I need an average temperature and an average deviation factor. Okay, so in that case, I need to make an average of the segment. Okay, so here I made an average of the temperature for the segment, taking the temperature at one depth, the temperature at another depth, and I make an average. Okay, so that's this cell here. And after that, to calculate Z, I also use the average temperature and the average pressure of that segment. Okay, but after I calculate pressure, okay, after I calculate pressure along the pipe, I don't need any more segment. I forget about it. Okay, the segment, I only use it to calculate CT and S and to calculate pressure. But after I have pressure in every place in the pipe, I don't need any more segment. I can do all calculations in a given point. Okay? So now we have, at that point we have pressure, we have this deviation factor. Now we can calculate this BG, right? And BG, the equation is, this is exactly the same exercise we have done the first day. Okay? We have the pressure, will be here, the temperature, what units should I use it? Yeah, let's see, let's check once more what are the units of that. BG is using Celsius, so I have to take once more. So let's see, BG, it will be the pressure, it will be the temperature, not average, okay, the temperature of the point, minus 273.15 to put it in Celsius. The set, I use the set of the point, this set, okay, and the unit will be 2, okay, and you see at least the number, the order of magnitude is, it sounds reasonable, okay, 3 to the minus 2. And we drag it down, okay. BG will be pressure, the temperature in Celsius, which is this guy here, B15, J15, yes? Because the temperature has to be in Celsius, okay, and here is in Kelvin, okay, but that's if you go to the function, Alt F11, you will see that it requires the pressure, the temperature in either in Fahrenheit or Celsius, okay, so it has to be now the Q local, how do I calculate the Q local? Is simply BG times the standard condition rate, right? And block it is the same rate for every location in the pipe, and then I drag it down. So you see it's actually increasing when the pressure goes down, which makes sense. Okay? It's increasing when the pressure goes down. You know, we are close to the, we have 6 minutes to finish. So I suggest we keep the rest of the exercise for tomorrow, if you agree. Yes? Because now that we have still some more things to do, okay? We have to calculate with the local rate the velocity, and then this velocity we have to calculate the erosional velocity and the liquid loading velocity. And we have to verify that it's higher, okay? We don't are above these limits. So we still need like maybe another 15 minutes. So I suggest we stop here, break here. You think about it the whole night. Let it, soak in the brain, and we make a summary tomorrow of what we have done. But basically, it's the same tubing equation, right? But we are applying it now on a segment because we are not interested in the inlet or outlet of the tubing. We are interested in what happens along the tubing. Mhm. And that's very useful for many things, okay? Actually, in multi-phase flow, we have to do our calculation in this manner, okay? Yes?
Check the video. I love to check the form of the average. I expect that
This one here?
yes, is the same.
Yeah, it's the same for all. Okay, so save this file and keep it on your computer because we are going to use it tomorrow. Okay? Before we close, any question? Many questions? Okay, see you tomorrow.